In the last two videos, we saw that with very large atoms, you can sometimes fit more than 8 electrons around the central atom. Now, generally when you're in the second period, the second row in the periodic table, an octet is the most that you can have. But it is possible with 2 atoms in the second row, beryllium and boron, to have an incomplete octet. An incomplete octet is less than an octet, less than 8 electrons on the central atom, which you're only going to see with structures that have beryllium or boron in the center. Now let's see how incomplete octets work. Here is a compound that is kind of in the twilight area between an ionic compound and a molecular compound. The electronegativity difference is such that this is kind of an ionic bond, but it's got a lot of covalent character in it too. So we can do a Lewis structure with this rather than doing an ionic structure like you would expect. So beryllium is unusual that way. Now, what do you think should be in the center of the structure? Well, that's kind of tough. One of the clues that I gave you in the last video was when you start out a formula with an atom, usually that's the central atom that they're starting it out with. Almost always that's the central atom. They're telling you that by writing the formula that way. So, step 1, skeleton structure. It's going to be a beryllium in the center and a chlorine on the outside. Step 2, count the valence electrons. Well, let's see. Chlorine has got 7 from the periodic table. And what does beryllium have? Beryllium has 2. So I get 16, right? Step 3, connect the structure. Okay, let's write our skeleton. And now let's connect it. I took away 4 electrons there. 16 minus 4 is going to be 12 left. Step 4, satisfy the outside atoms. Okay, each of these chlorines has got 2, and they want to have an octet, 8, so they need 6 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I took away 12, and I've got none left. 5, dump the remaining electrons on the central atom. Okay, well I have no remaining electrons to dump there, so that's what I've got. Now, if I was a B student, what I would do, I think, is say, at this point you're asking, is the central atom satisfied? So the recipe would tell you, well, no, because it needs 8. So the recipe would say, if your answer is no, if that's not satisfied, then form multiple bonds. But this is a case where the recipe leads us astray a little bit, because if if I go ahead and do that, I can give beryllium an octet. I mean, I could do it a couple different ways. I could share an electron pair here and share an electron pair there and get a structure that looks like this. Or I could share it on one side, two pair on one side, and get a structure that looks like this. Or I could share a pair here and a pair here and get a structure that looks like this. So I'm getting three possible structures here. Whoops. Nothing up there, just two dots there. Now if I look at any of these structures, and go ahead and you look at them yourself, and let's just look at one of them. They all have very high formal charges. They all have terrible formal charges. If we look at the formal charge on the chlorine here, chlorine has 7 minus 1, 2, 3, 4, 5, 6, 7 minus 6. It's got a plus 1 charge. This one is the same, so it'll have a plus 1 charge as well. So you're putting a positive charge on a very electronegative atom, which is a bad thing to do. And let's look at the beryllium. On the periodic table it has 2 valence electrons minus 4, which is going to be minus 2. So this has a minus 2 formal charge, and these have plus 1s. Those are high overall formal charges. It's not so good with these structures either. You're still going to have a minus 2 formal charge on the beryllium for each of these. You're going to have what kind of charge on this? 7 minus 5 sticks and dots is a plus 2. And then this one's going to be 7 minus what? 1, 2, 3, 4, 5, 6, 7 is 0. But, I mean, you have a 0 on this chlorine, but look, you got a minus 2 and a plus 2 here. That's no good. This one will have a 0 formal charge on the chlorine here, but a plus 2 formal charge there. So all three of the structures that we generate with the recipe are giving us terrible formal charges. Now there's a way to fix this, and this is kind of analogous to what we did in the last video. You can leave an incomplete octet on beryllium and boron and it will be satisfied. Beryllium is satisfied not with an octet, but with 4. And boron is satisfied not with an octet, but with 6 electrons. Let's put a box around this. This is the key to understanding structures, how to fix structures that have boron or beryllium in the center. They have incomplete octets. Let's see what kind of structure we would have had here. And in fact, we don't have to do all this extra work. We did more work than we needed to, because if beryllium is satisfied with just 4, when we asked, is it satisfied, we should have said not no, but yes, because it's satisfied with only 4. And that would mean we were done here. Let's convince ourselves that we were done when we hit that structure. We went too far. If I look at the formal charge on this, it's 2 minus 2 sticks is 0. If I look at the formal charge on chlorine, it's 7 minus 7 sticks and dots, it's 0. And then this chlorine is 0 too. So 0 formal charges all around. This is the structure for BeCl2. Now, let's do one with boron. And let's keep in mind this little addendum to the rules here, that when we have beryllium or boron, they are satisfied not with an octet, but with an incomplete octet. Let's do Bf3. Okay, step 1, skeleton structure. Okay, I'm going to put the boron in the center because it's closer to the center of the table than the fluorine. So there's my skeleton. Let me move it down so you can see it. And now I'm going to count the valence electrons. Okay, let's see, boron has got 3 from the periodic table. See? And fluorine, there's 3 of those, and they each have 7 from the periodic table. So 3 times 7 is 21, plus 3 is 24. So I have 24 electrons to work with. Step 3, connect the structure. Okay, let's write our skeleton down and connect it. I drew 3 bonds in there, so that took away 6. So I have 18 electrons left. Step 4, satisfy the outer atoms. Okay, each one wants 8. It's got 2 already from that stick going into it. So it needs 6 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I took away 18, and that's what I had. Now I have none left. Now, dump the remaining electrons on the central atom. Now, I don't have any to dump, so I don't have anything to do there. And I ask, is the central atom satisfied? Before you watched this video, you would have said no, because there's only 6 and it wants 8, you would think. But remember, boron is special. It's an exception to the rule. Beryllium and boron are satisfied with an incomplete octet. Boron is satisfied with 6, so you would say yes. And that would mean you were done there. That would mean you wouldn't have to go any farther. This is the answer. This is the structure. If you did go any further, you would get a structure maybe that looks like this. If you said no, you'd try to give it an octet by doing something like this. And if you did that, you could see that you were wrong, because when you look at the formal charges, boron's formal charge will be 3 minus 4 is a minus 1. And then fluorine's formal charge here will be 7 minus 1, 2, 3, 4, 5, 6 is plus 1. Now, remember, fluorine is the most electronegative atom on the table. It is the most electron-greedy element that there is. And it's not going to put up with you giving it a plus 1 charge in a structure. This will never happen. You will never see a plus 1 charge on a fluorine. So this structure can't be correct. This one is the correct one.